Welcome again to GM Tutorials. My name is Shahruh Yahyayev, and now we're gonna discuss strong mathematical induction. Of course, in the previous video, I hope you watched and understood what mathematical induction is, and basically, this is what actually you need for your final exam. Strong mathematical induction is a special case. Mostly, you use just simple mathematical induction, but sometimes you may come to know that it's better to use strong mathematical induction. The idea is the same, but there's some kind of additional, not steps, but cases, let's say. So, idea is the same. You have a step 1 and step 2. We're not gonna see any example. I'm gonna just give the theory because it's so simple. There's one additional kind of thing that we add to the step 2. Okay, so step number 1, as you know, no, let me write it not here but from here. Okay, step number 1. Of course, this is base step. So in this base step, as usual, you prove for initial case. Okay, this I initial case or what the number doesn't matter, and you prove that for P1. Okay, so assume that we have this Pn expression, right? And for n equals to 1, etc. So you have to prove that for this value of n, the certain statement is true. So firstly, you prove it for initial case, not 1 but I equals true, okay, or is true. So done. The step number 1 is the same, but in the step number 2, you now, okay, firstly, let me remind you that in step number 2, in inductive step, in just simple mathematical induction, you assume that for, assume that for n equals to k, pk is true, right? Do you remember? Yeah, and then in the next step of the step number 2, we had to prove kind of pk plus 1. So first we assume that it's true for pk, then we assume for pk plus 1, and that leads to the proof that for n also this expression is true. So, but in this case, in this strong mathematical induction, you assume not only just k. I mean, you don't assume that this is true for only pk. No. You assume that. Okay, so. Okay, you assume that for n in the range. Okay, for n in the range I less than n, but n is less than k. Okay, so I is initial case, right? Initial case, this I. So now you assume that this statement is true for all values in this range, for all values in the range. Okay, for all values in the range, the statement is true. Then, as usual, you prove the case or the statement for n equals to k plus 1 case. So you may ask a question, why we should kind of assume not just the k but this range, because sometimes you may need to also kind of the values of previous steps, previous elements, yeah, while proving k plus 1 case. That means, okay, assume that you are proving this k plus 1 case, and somehow in expression you have this one, k minus 1, okay, and plus k minus 2. Okay, if you just assume that only pk is true, I mean, only when n equals to k, like in simple mathematical induction, then how do you know that? I mean, how you can prove without knowing whether the statement is true for k minus 1 or k minus 2 or k minus m, okay? So thus, you assume that this k minus 1 and this k minus 2 is, or not is, but they both, let's come here together, they are both in this range. So that means the statement for these cases are true, and that leads that k plus 1 case is also true, and finally pn is also true. I hope you got my point. So this is all. So now you know also what strong mathematical induction is. So wherever you need the values of previous elements, please use not simple mathematical induction. You can't use it actually, but use strong mathematical induction. So remember this one and this one. See you soon in our next tutorials.